Hello, Math 30-1. Welcome back to Functions and Relations Lesson 2. And in this lesson, we're gonna be talking about some of the operations we can have with pairs of functions. So the following properties apply if you have f and g, and provided x is in the domain of both f and g. That's an important mathematical statement, and I want you to ponder that, and I will ask you about that. That's a kind of a deeper thing. We'll talk about that more in class. If you have two functions and somebody says to add them, that's the way they would ask you to do it. And that means that you should add the two functions together. If they want the difference of the functions, they might say f minus gx, and that's what it would look like. And product would be f gx, and that's how it would look, and so on. So now if we consider in this lesson, we're only going to look at the sum of these. I want you now to look at that table of values, and as it says in example 1, to investigate, right? This is your job. I want you to play and get messy. And I want you to plot f at x, plot the x and f at x values, and plot the x and g at x values on the chart, look at the graph, and then also complete the tables for f plus g at x. When you come back, you can have a look and see how it looks and how those things fit together. So I want you to investigate, go on your own, pause the screencast, and do it yourself. Well, as you can see, those are your two graphs. If you just plot those points, that was quick and easy. And now clearly, if we fill in the table of values, what is f plus g at x? Well, clearly this is minus 14, minus 11, minus 8, minus 5, minus 2, 1, 4, 7, and 10. And if we consider, well, what's f minus g at x? Well, this is 0, this is 1, this is 2, this is 3, and again, it's f minus g. This is, this is 4, 5, 6, 7, 8. And we can clearly see that the difference. Now, when you think about what's that going to look like when we graph it, well, you can maybe already have an idea what that looks like, but I want you to go to the graph and graph those two new functions and then see how that compares. So when you look at the graphs, clearly, I mean, it's really straightforward to graph the blue line, the f at x. It's really straightforward to graph the g at x. When you plot the two, how does, say, the red graph, which is f plus g, relate to the other two? And you might wonder, well, one of the things I'd like you to ponder is why does it go up by 3s when the other ones didn't? Why is that one going up by 3s? Well, if you think of it, it's the combination of f plus g at x, and the blue graph is always going up by 2s every x value, right? It's always jumping by 2s, the blue graph, and it jumps by 2s every point, and the green graph jumps by 1. So when you think of it, what would the red graph do? Well, the red graph is going to jump by 3s because it is got the sum of the slopes of the other ones, really, because it's a linear graph. So that's kind of interesting. If you look at the blue circles, that's the graph of f minus g at x. Now, the question you might ask is, why has this got a value of 0 right here? Why is f minus g at -4 equal to 0? Why is that point right there? Well, that's because there is no difference between the graph, and if we measure the difference in the graph between the distance between the two y values, that clearly at this point right here, there is no difference between green and, blue and green. And so the difference is 0. And at this point, the difference is 1. And at this point here, the difference is 2. And at this point, the difference is 3. And so that's kind of cool. That's why it works that way. Carry on with your play, and we go to the next page. So the functions f and g have on the previous page are f at x, 2x plus 1, and g at x. Write the expressions for the functions. So now we actually get to put real functions, not just a table of values. So what is f plus g at x? Well, clearly that's just simply going to be 2x plus 1 plus the x minus 3, which would obviously be 3x minus 2. And what is f minus g at x? Well, I'm not going to write them both up, but f minus g at x is 2x minus x, which would be x, and 1 minus minus 3 would be plus 4. It says using the graphing calculator to graph f plus g at x and y equals from part D, compare these graphs. Compare with the graphs in part C. Well, clearly we should get the same value. And it's a nice, easy way to do this is if you put y1, as equal to f at x, and if you put y2 equal to g at x, then when you want to graph the sum function, for example, f plus g at x, just a little hint how to do this with your calculator, then you can just graph y3 is equal to y1 plus y2. So it's another way of doing this same notation. And the same for f minus g at x. You can type them in separately and then add and subtract as you want. When we state the domains for it, clearly both domains are x's and on the root. They're lines. They're all lines. And clearly the range are y such that y is an element of reals as well. When we determine the values for f plus g at x at 10, I can clearly just look. It's much easier. Even I don't even go to my graphing calculator. I could actually just look f plus g at x. If I just plug in 10 right there, f plus g at 10 would be really equal to 3 times 10 minus 2, which is really 28. And if I want to know f minus g at 10, I can simply go to this function right here, and f minus g at 10, or minus 10, sorry, minus 10 would clearly be minus 10 plus that 4, which would be equal to minus 6. So it's much easier to just use those functions. And then go to your calculator. In this example, the sum, so as it says, some functions, when you add or subtract them, you get the same thing. You get lines. If you started with degree 1 functions, you add and subtract them, you get degree 1 functions when you add and subtract. But that's not always the case. Try and think of one that isn't going to work that way and come back and try. So just pause for a second and explore and try out H. Can you think of something that degree 1 but doesn't turn out to that? So you might have drawn a blank or you might have come up with something, but here are two linear functions. They're special lines. They're actually, these first two are parallel lines. And if you think of it, in these two, and this question here in H, the first example I gave you, are two lines that are parallel. One has a y-intercept of 2 and a slope of 3, and one has a y-intercept of -7 and a slope of 3. So this is this is G, and this one here is F. Now, if you think about it, if you subtract the two y values, you'll always be 9 apart. And so if you go F minus J, the difference between those two functions will always be 9. So the difference function isn't linear, it's actually a constant function. And the other example is if you had two lines that were not parallel but perpendicular. Now in that case, if you add those two functions, you will always get a constant, because one line's always going up by 3 and the other line's always going down by 3. So the sum of the two will always be 7. It'll be a constant. So in this case, the sum is not the same. At this point, I would like you, we've investigated a little bit about the linear ones. I would like you to move to example 1 of, to skip past this part 2 investigation and move to example 1 to give the sum and difference a try with not just a linear function, but a quadratic function. So please have a look at example 1 and give it a try. So in example 1, it says to determine an expression 4. So again, we've learned what f at x plus g at x means. That's a fancy way. I'd like you to use a notation. What am I doing? Well, they're asking me to write an expression for f plus g at x. I can write it all out, but I think we can see that if I add these two functions together, I will have 2x cubes. I will have minus 2x squared. I will have minus 2x's, and I see a 6 plus 6 is 12. So if I add those two functions together, that's what I get. In the second one, they want me to do f at x minus g at x. So that, in a little simpler, not simpler, but more succinct terms, would be f at x minus g at x. And if I subtract those two, make sure you go in the right order, clearly x cubed minus x cubed, that blows up. And what's important, and I am going to take the extra time to just write this one out, you need to be careful about distributing subtraction. So x cubed minus 2x squared plus 6, that part doesn't matter so much as the fact that you are subtracting all of this term. So x cubed minus 2x and positive 6, and you need to be careful about the fact that that's subtraction. So that goes way back. We could get rich if everybody had to pay a a distributive property fine for not doing that right. So clearly we'll have no x cubes minus 2x squared plus 6 minus x cubed plus 2x and a minus 6. And so as we look through what's left, we're going to have a minus 2x squared. The x cubes blew up, and we have a plus 2x, and the 6's blew up, right? So it says complete the following statement. Ponder that. You can pause, and you don't have to just copy this. You can do this at your own pace. F of x plus gx is a sum of two functions, f and g, and can be rewritten as f of x plus gx is equal to f of x plus g of x. F of x minus gx is a difference of two functions and can be rewritten as f minus g of x. Just different ways of writing the same thing. Equal to, in this case, oopsie, I'm sorry, and can be written as, this was supposed to be our answer from above. So the sum was 2x cubed minus 2x squared minus 2x plus 12. And the difference of two functions can be written as f minus g of x, and in this case it was minus 2x squared plus 2x. And I think I said squared here, but I wrote cubed. All right, so now if we evaluate what is f plus g at 2, we simply use that simplified function. So f plus g at minus 2, you will go through the cubic function and type in 2 times negative 2 cubed minus 2 times negative 2 squared, 2 times negative 2 plus 12. And you need to be careful with all those negatives there. And if it all goes well and you do that right, we end up with negative 8. Now, we don't always have really nice numbers, so f minus g at root 6 would be minus 2 times the root 6 squared plus 2 times root 6. And radicals are nice numbers as well, irrational numbers, so we need to be aware that that's really just minus 12, and this is plus 2 square root 6. And we need to leave it like that because there's nothing we can really do. All right? All right. I want you to read example 2. Give it a try on your own and come back to the screencast as you need it. But give that application a try on your own. So example 2 is kind of a nice application, a bit of a business application in economics. And if you ever get the pleasure of taking an economics class, it's got a lot of graphs and you're adding and subtracting them and so on. So in this case, what is the cost function? What does it cost for every unit that we produce here? Well, if you read carefully, it costs $10,000 no matter how many you produce. Plus, they're going to charge you $3 for every one after that. In terms of revenue, how much money can we make? Well, revenue is equal to $15 per every unit. The company's profit then is really about C at X. Whoopsie, I'm sorry. It's really about revenue minus your costs. And in that case, it's going to be 15x minus the original function of 10,000 plus 3x. And that would clearly give us 12x minus $10,000. And the question is, determine the company's profit for 20,000 DVDs produced. Well, clearly, we just want to find profit when we substitute in 20,000. And when we do that, we get a total of $230,000 in profit. Well done. Please follow the assignments that were suggested in your formative assessment handout. Well done, Math 30. Please ask any questions next day as we try the assignments.